The largest known structure in the observable universe is not a galaxy cluster, not a wall of stars. It is an almost completely empty region of space 330 million light-years across. And it is still growing. Subscribe if you want more of the cosmos. This is white space. Settle in. There exists a boundary where human intuition quietly fails. We can picture a kilometer, a 10-minute walk across a familiar city. We can imagine 1,000 kilometers, the distance between two capitals crossed in an hour by aircraft. But when numbers climb into the billions and the units themselves become light years, the mind finds no foothold. The cosmos does not ask permission to be incomprehensible. And yet astronomy has made the incomprehensible observable through measurement, calculation, and instruments launched outward into the dark. Science has traced the outlines of structures so vast that to name their dimensions is to speak almost in the language of metaphor. Today, we will follow a path through scale itself. It begins close to home with a planet whose ring system stretches nearly 300,000 kilometers from edge to edge, a world so extravagant in its beauty that it seems designed for effect rather than function, and yet has followed its orbit around our Sun for 4 billion years without interruption. From there, we move outward, step by immense step. We will encounter a young planetary system caught in the act of formation, a disk of gas and dust encircling a nearby star, where worlds are still assembling themselves from raw material. We will visit a star so massive and unstable that the forces contained within its outer layers exceed the power of any weapon ever imagined, a star standing at the threshold of annihilating itself in an explosion visible across the galaxy. We will examine one of the largest known stars, an object so enormous that placing it in the center of our solar system would swallow every planet out to Jupiter. Then we will step beyond our galaxy entirely toward a spiral that contains 40 billion suns and bears its own extraordinary secrets. And finally, we will arrive at the edges of the observable cosmos, where the largest structures in existence turn out to be made not of matter, but of emptiness, vast voids spanning hundreds of millions of light years, whose origin science is only beginning to understand. This is a journey through the most colossal objects known to astronomy. Prepare yourself, it begins now. Saturn, the sixth planet from the Sun, sits at an average distance of 1.5 billion kilometers from our star, so remote that sunlight, traveling at 300,000 kilometers per second, takes more than an hour and 20 minutes to reach it. And yet, even from such a distance, the planet is immediately recognizable. No other world in the solar system presents itself quite so dramatically. The rings of Saturn have been visible in amateur telescopes for 4 centuries, since Galileo Galilei first turned a primitive glass toward the planet in 1610 and reported with bewilderment that it appeared to have ears. It would take another 50 years before the Dutch mathematician Christian Huygens correctly identified those ears as a flat disk encircling the planet, a ring system of such improbable dimensions that subsequent generations of astronomers have never quite stopped marveling at it. The visible ring system extends across roughly 280,000 kilometers, a span wider than the distance from Earth to the Moon. Yet this extraordinary breadth coexists with an almost unimaginable thinness. In most places, the rings are no more than 10 to 30 meters from top to bottom. If you were to scale the ring system down to the width of a standard sheet of paper, the paper itself would be thousands of times thicker than the rings are proportionally in space. This geometry creates a startling optical effect visible even from Earth. When Saturn's orbital path carries it to a position where its rings lie edge onto our line of sight, the entire ring system seems to vanish. The planet appears almost naked, a pale ochre disk floating without ornament against the stars. Then, as the orbital geometry shifts over the following years, the rings gradually return, tilting toward us and brightening until Saturn blazes at its most spectacular. The rings are not uniform. They divide into distinct bands separated by gaps, and these divisions carry their own names, their own histories of discovery, their own physical explanations. The Cassini division is the most prominent of these gaps. A dark band roughly 4,800 kilometers wide, separating the brighter outer A ring from the massive B ring beneath. Its existence puzzled astronomers for centuries after Giovanni Cassini first observed it in 1675. The explanation finally arrived at through orbital mechanics is elegant. A particle orbiting Saturn at the distance corresponding to the Cassini division completes exactly 2 orbits for every single orbit completed by the moon Mimas. This gravitational resonance means that Mimas exerts a steady periodic tug on any material in that zone, nudging particles out of position and gradually clearing the region. The division is not a gap in the conventional sense. It still contains material, but the density there is dramatically lower than in the adjacent rings. The B ring is the brightest and most massive component of the entire system. It begins roughly 25,000 kilometers from Saturn's visible upper atmosphere and extends outward for an additional 25,000 kilometers, a band of icy particles ranging from fine powder to objects several meters across. Despite its visual dominance, the B ring is astonishingly thin. Its vertical extent reaches at most 10 meters through most of its extent, though the outer edge buckles into ridges up to 2.5 kilometers tall, where gravitational resonances compress the material into corrugated walls. The A ring, outermost of the prominent bands, contains some of the most dynamically interesting features in the system. Within it moves a small moon called Daphnis, an elongated body only 8 kilometers across, which maintains a narrow channel called the Keeler Gap with extraordinary precision. As Daphnis travels through this cleared lane, its gravity draws waves into the walls of ring material on either side, creating sinuous undulations that resemble, under the right lighting conditions, the wake behind a ship crossing a still harbor. Beyond the A ring, largely invisible in optical light, lies the F ring. This narrow band sits just outside the outer edge of the A ring, and it owes its peculiar braided appearance to 2 small shepherd moons, Prometheus and Pandora. Prometheus orbits just inside the F ring, and with each close pass, it reaches gravitational fingers into the ring material, creating transient channels and streamers that reform, tangle, and evolve in complex patterns over the course of months. The F ring is less a ring than a dynamic negotiation between the material and the objects that confine it. The total mass of all of Saturn's rings together is estimated at roughly 3 × 10 to the 19th power kilograms, approximately 20,000 times less than the mass of the Moon. The material is overwhelmingly water ice mixed with small quantities of rocky silicates and trace organics. Where the ice is purest, the rings reflect sunlight brilliantly. Where contamination darkens the particles, the material appears brownish and gray. The origin of the rings remains an active area of debate. One prominent hypothesis holds that the ring material represents the shattered remains of a small icy moon, torn apart by tidal forces when it wandered too close to Saturn's gravity well. Another suggests that the rings may be remnants of the original protoplanetary disk from which Saturn itself formed. The relative youth of the rings inferred from the clarity of their eyes suggests they formed no more than 100 million years ago, long after the dinosaurs had already walked the Earth. Saturn's moons, of which there are now more than 140 confirmed, orbit through and beyond the ring system, and each presents its own extraordinary individuality. Mimas, the smallest of Saturn's round moons, is best known for an enormous impact crater that dominates one entire hemisphere. The Herschel crater stretches 130 kilometers across, roughly a third of Mimas's total diameter, and gives the Moon an unsettling resemblance to the famous station from science fiction. The crater's central peak rises 6 kilometers from the floor, and its walls plunge 10 kilometers to the base. Whatever created Herschel struck with an energy that was barely insufficient to shatter the moon entirely. Fractures visible on the side directly opposite the impact suggest that shock waves propagated all the way through the body and very nearly broke it apart. Dione, somewhat larger, presents a more geologically complex face. Its trailing hemisphere is covered by a network of brilliant white streaks, thin cliffs of exposed ice, tens to hundreds of kilometers long, created when Dione's interior contracted and the outer crust fractured along fault lines. These features, originally called wispy terrain, when observed at low resolution by the Voyager probes, were revealed by the Cassini spacecraft to be sheer icy scarps, some reaching hundreds of meters in height. Subtle measurements of Dione's gravitational field during close flybys have raised the possibility that a liquid water ocean may persist beneath its frozen surface, making it one of several outer solar system moons now suspected to harbor conditions potentially relevant to chemistry far more complex than ice. Rhea, the second largest of Saturn's moons, is composed almost entirely of water ice. Its surface is ancient, scarred by billions of years of impact cratering across virtually every square kilometer. In 2008, data from the Cassini spacecraft suggested a faint ring system around Rhea itself, which would make it the first moon in the solar system known to possess its own rings. The claim remains tentative, and the question has not been definitively resolved, but the possibility alone illustrates how much complexity persists even in well-studied systems. Between Rhea and the outer moons lies Titan, Saturn's largest satellite and the second largest moon in the entire solar system, exceeded only by Jupiter's Ganymede. With a diameter of 5,152 kilometers, Titan is actually larger than the planet Mercury, though less massive. It is also the only moon in the solar system possessing a dense atmosphere, and the only world other than Earth known to maintain stable bodies of liquid on its surface. The atmosphere of Titan is approximately 1.5 times denser than Earth's at sea level, composed primarily of nitrogen with a significant fraction of methane and traces of dozens of other organic compounds. The nitrogen atmosphere is deep enough and optically thick enough that the surface of Titan was entirely hidden from direct optical observation until the Huygens probe, released by the Cassini spacecraft, descended through the clouds in January 2005 and transmitted images of a landscape covered in rounded pebbles of water ice, colored orange-brown by hydrocarbon deposits. The temperature at Titan's surface is approximately 94 Kelvin, minus 179 degrees Celsius, and at this temperature, water is a solid rock. The liquid that fills Titan's lakes and seas is not water, but methane and ethane, hydrocarbons that exist in liquid form at these extreme temperatures. The largest of Titan's liquid bodies, Kraken Mare, is estimated to cover an area comparable to the Caspian Sea, making it by far the largest extraterrestrial liquid body discovered in the solar system. Radar mapping by the Cassini orbiter revealed a shoreline geography of remarkable complexity: bays, inlets, islands, and what appear to be deltas where river channels discharge into the larger seas. The methane cycle on Titan functions as an analog to the water cycle on Earth. Methane evaporates from the surface, rises into the atmosphere, condenses into clouds, and falls as methane rain. Droplets that, at Titan's gravity and atmospheric density, fall more slowly than rain on Earth and are somewhat larger. In equatorial regions, which are generally drier, this rainfall occurs episodically, driving brief but intense floods that carve drainage networks through the icy landscape. In polar regions, methane precipitation is more consistent, maintaining the large liquid seas. The interior of Titan is believed to contain a layer of liquid water mixed with dissolved ammonia beneath its thick ice shell. An ocean that may have persisted for billions of years, kept liquid by the combination of tidal heating from Saturn's gravity and the antifreeze properties of ammonia in water. Whether this subsurface ocean could support any form of chemistry complex enough to be called life is an open question. The same question applies, perhaps more plausibly, to the methane lakes at the surface. Could exotic biochemistry operate in liquid methane rather than liquid water, using entirely different molecular scaffolding? This remains entirely speculative, but the question itself illustrates how radically our conception of the conditions necessary for complex chemistry has expanded as we have studied the outer solar system in detail. Titan's future, like that of all objects in the solar system, is tied to the eventual evolution of the Sun. When our star expands into a red giant in approximately 5 billion years, the increased luminosity will warm Titan dramatically. The thick nitrogen atmosphere will be supplemented by the evaporation of surface and subsurface materials. And the Moon may undergo a brief geological epoch of conditions superficially more familiar to life as we know it. Liquid water on the surface, a warmer and more chemically active environment. Before the Sun's expanding atmosphere eventually engulfs the inner planets and sends destructive levels of radiation throughout the system. Then there is Hyperion, a moon unlike almost any other in the solar system. Hyperion is roughly 300 kilometers across but distinctly non-spherical, resembling a lumpy, pockmarked sponge more than any conventional conception of a moon. Its surface is covered in deep, sharp-edged craters with an unusual depth-to-diameter ratio that gives it the appearance of compressed foam. The most remarkable thing about Hyperion, however, is its rotation. Unlike virtually every other large moon in the solar system, Hyperion does not rotate in a predictable, tidally locked manner. Instead, it tumbles chaotically in 3 dimensions, a behavior confirmed by repeated observations and explained by its irregular shape combined with the gravitational influence of nearby Titan. Hyperion spins like a thrown object. No equation of its future orientation is reliable beyond a few weeks. And finally, Iapetus, the moon that Giovanni Cassini himself observed to be clearly visible on one side of Saturn, but invisible when it had moved to the other. The reason is one of the most visually striking contrasts in the solar system. One hemisphere of Iapetus is coated in one of the darkest materials found anywhere in the outer solar system, a reddish-brown organic compound with a reflectivity barely exceeding that of charcoal. The other hemisphere is nearly as bright as clean snow. The current explanation attributes the dark coating largely to micrometeorite bombardment and the inward spiral of reddish dust from outer irregular moons, with thermal migration subsequently concentrating the dark material on the leading hemisphere. But what makes Iapetus doubly strange is its equatorial ridge, a mountain range running precisely along the equator for more than 1,300 kilometers, with peaks reaching 20 kilometers in height. No confirmed counterpart to this ridge exists anywhere else in the solar system. Its formation remains incompletely understood. 63 light-years from our Sun in the southern constellation of Pictor, a young star burns with an intensity roughly 9 times greater than the Sun's own luminosity. It is known as Beta Pictoris, and by astronomical standards it is extremely young, somewhere between 8 and 20 million years old. For comparison, our own solar system completed its initial formation approximately 4.5 billion years ago. What makes Beta Pictoris remarkable is not the star itself, but what surrounds it. In 1984, astronomers examining the star in infrared wavelengths discovered something unexpected: a vast disk of gas and dust extending outward for more than 1,500 astronomical units from the star. This disk, seen edge-on from our vantage point, became the first protoplanetary disk ever directly imaged around another star, and it transformed understanding of how planetary systems form. The disk is not a flat, uniform sheet. Detailed observations with the Hubble Space Telescope revealed that the inner and outer sections are slightly warped relative to each other. This warp is understood to be caused by the gravitational influence of a massive planet embedded within the disk. That planet, designated Beta Pictoris b, was directly imaged in 2008 and confirmed in 2010, making it one of the earliest exoplanets captured in direct photographs. Beta Pictoris b is a gas giant roughly 10 times the mass of Jupiter, orbiting its parent star at approximately 9 astronomical units, similar to the distance between our Sun and Saturn. The disk itself is in constant visible motion. Measurements of absorption features in the star spectrum reveal that comets and small rocky bodies are continuously falling inward toward Beta Pictoris, evaporating as they approach and adding their vapors to a complex chemical environment. These infalling bodies are sometimes called falling evaporating bodies, and their abundance suggests that the Beta Pictoris system is currently passing through a phase analogous to the late heavy bombardment of our own solar system, experienced roughly 3.5 to 4 billion years ago, a period of intense meteorite impacts driven by the gravitational migration of the giant planets. Within the inner disk, photometric monitoring of the star has revealed additional structure. In 1995, Beta Pictoris b transited across the face of the star as seen from Earth, producing a prolonged dimming effect. But this transit was caused not by the planet itself, but by a disk of material surrounding the planet, a circumplanetary ring and dust structure that swept across our line of sight over a period of several years, allowing astronomers to map the structure around the giant planet in remarkable detail. The Beta Pictoris system gives us a window into the past. The materials circling this young star are the raw ingredients from which worlds assemble themselves. Whether the planets forming here will eventually bear the same diversity of composition and orbital architecture as our own solar system cannot yet be known. What is certain is that this system is actively in the process of building something. From Saturn, a mature planetary system whose ring architecture reflects 4 billion years of gravitational sculpting, to Beta Pictoris, a system still in the chaos of formation, we begin to appreciate that what we observe in any given planetary system is always a snapshot in time. The cosmos is never finished. Every structure we see is in the middle of becoming something else. In the winter sky visible from the northern hemisphere, the constellation Canis Major rises in the southeast, dominated by Sirius, the brightest star in the night sky, a nearby beacon blazing with the light of roughly 25 suns. Sirius is spectacular by any measure, but buried in clouds of interstellar gas and dust nearly 5,000 light-years from Earth. In the same constellation, there is an object that makes Sirius look almost negligible by comparison. It is designated V Canis Majoris, and for a substantial portion of the early 21st century, it held the title of the largest known star in the observable universe. The first challenge in understanding V Canis Majoris is grasping its scale. Current measurements, refined through interferometric observations and spectroscopic analysis, place the radius of V Canis Majoris at approximately 1,400 to 1,500 times the radius of the Sun. If this star were placed at the center of our own solar system, its surface would extend beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, Mars, the asteroid belt, and the gas giant that governs the outer solar system, all beneath its outer layers. Light traveling at 300,000 kilometers per second would require more than 6.5 hours to circle this star's equator. V Canis Majoris is classified as a red hypergiant, the most extreme category of stellar evolution, occupying the upper right corner of the Hertzsprung-Russell diagram, where luminosity and radius reach their maximum possible values for objects that are still, technically speaking, stars. Its surface temperature is approximately 3200 Kelvin, less than half the temperature of our Sun. This relatively cool surface accounts for its deep reddish color and means that its enormous luminosity, estimated between 200,000 and 450,000 times the Sun's output, is radiated predominantly in infrared wavelengths. Vi Canis Majoris is not merely large, it is also extraordinarily unstable. The outer envelope is in constant turbulent motion, driven by convective processes of a violence that dwarfs anything in other stellar objects. A single convective cell on the surface of Vi Canis Majoris might span a volume larger than the entire Sun. These cells carry hot plasma from deep interior layers upward to the surface, where it cools and falls back, creating surface features that have been photographed as actual bright and dark patches against the star's disk. An astonishing achievement, given that Vi Canis Majoris subtends only about 2 milliarc seconds on the sky, barely within the resolving power of modern interferometers. The star drives an extremely powerful stellar wind, an outflow of material from its surface that carries away mass at rates unmatched by any other known type of star. Vi Canis Majoris loses approximately 30 times the mass of Earth every single year through this continuous outpouring. The total mass ejected over the course of its evolution has built up a complex asymmetric nebula around the star, an envelope of gas, dust, and molecular material extending outward, for thousands of astronomical units. This nebula is not a simple symmetric shell. It contains arcs, knots, and bow shock structures that record a history of episodic mass loss events in which the star shed entire shells of its outer envelope over the course of hundreds to thousands of years. The chemical richness of this circumstellar environment is striking. Spectroscopic observations have identified dozens of molecular species in the material surrounding Vi Canis Majoris, including water, silicon monoxide, sulfur dioxide, and a range of organic compounds, all synthesized in the photochemically complex layers of the outflowing wind. To understand how Vi Canis Majoris came to exist in this state, it is necessary to trace the evolution of the most massive stars. When a cloud of interstellar gas and dust containing perhaps 30 to 40 times the mass of the Sun begins to collapse under its own gravity, the central temperature and pressure rise dramatically. At some critical point, perhaps 100,000 years into the collapse, a thermonuclear reaction ignites at the core. Hydrogen nuclei begin to fuse into helium, releasing energy that exerts outward pressure against the inward pull of gravity. A star is born. For a star as massive as the progenitor of Vi Canis Majoris, this phase, the main sequence, lasts only a few million years. The more massive the star, the more rapid the consumption of fuel. Stars of this class burn bright and die young by astronomical standards. As hydrogen reserves are exhausted at the core, the thermonuclear engine shifts. Helium, accumulated at the center, begins to fuse under gravitational compression, releasing energy through different reactions. The star's outer envelope responds by expanding dramatically, and over a relatively short time. The star swells outward by factors of hundreds. Its surface cools, its color reddens. This is the transition to the red supergiant phase. In the most massive stars, nuclear reactions proceed through multiple stages. After helium comes carbon, then neon, oxygen, and finally silicon. Each successive fuel is more difficult to ignite, lasts for a shorter time, and leaves a more complex residue. The silicon burning stage, which produces iron at the core, concludes in a matter of days. Iron is the terminal product of stellar nucleosynthesis. Fusing iron nuclei requires an input of energy rather than releasing it. When the iron core accumulates to a mass approaching 1.4 times the mass of the Sun, the Chandrasekhar limit, the core's internal pressure can no longer support itself against gravitational collapse. What follows happens in less than a second. The iron core collapses at a quarter of the speed of light, in the space of a heartbeat. A region the size of a large city is compressed to a sphere 10 to 15 kilometers across, with a density equivalent to that of an atomic nucleus. The infalling outer layers strike this impossibly dense surface and rebound in a shock wave of staggering energy. Simultaneously, a burst of neutrinos carrying 100 times the total energy output of the Sun over its entire lifetime, released in just a few seconds, blasts outward through the collapsing star. The result is a supernova, an explosion that briefly outshines an entire galaxy. For V Canis Majoris, current estimates suggest this event may occur within the next 100,000 years, perhaps sooner, perhaps slightly later. The star's behavior offers few reliable clues. Its brightness varies on unpredictable timescales, and its outer envelope has already begun the process of pre-supernova mass ejection. When the explosion finally arrives, the resulting flash will be visible from Earth in broad daylight. The expanding shell of ejected material will evolve over centuries into a supernova remnant, seeding the surrounding interstellar medium with the heavy elements synthesized in the star's interior: calcium, iron, silicon, and traces of heavier elements like gold and uranium that can only form in the extreme conditions of a collapsing stellar core. At a distance of 5,000 light-years, the radiation from this future explosion will pose no direct threat to life on Earth. The intense gamma-ray burst accompanying collapse will be absorbed by the intervening interstellar medium long before it reaches our planet. The remaining compact object, a neutron star, or perhaps a black hole, will be left cooling at the center of an expanding luminous cloud. Even V Canis Majoris, however, may not hold the absolute record. In the dense star fields of the constellation Scutum, approximately 9,500 light-years from the Sun, there is a star so embedded in dust and so remote from Earth that it has never been visible to the naked eye. It is catalogued as U Scuti, and for a significant period of the early 21st century, it carried the strongest claim to being the largest star in the known universe by linear dimensions. Measuring stellar radii is not straightforward. Direct imaging of stellar disks lies beyond the resolving power of even the most advanced telescopes in most cases. Instead, astronomers combine measurements of a star's angular diameter, obtained by interferometry with its distance, derived from parallax or statistical methods. Both measurements carry uncertainties, and for a star as distant and dust-obscured as U Scuti, those uncertainties are substantial. With this caveat in mind, the most widely accepted estimates place the radius of U Scuti at approximately 1,700 to 1,800 times the radius of the Sun. If this measurement is correct, U Scuti is somewhat larger than V Canis Majoris, though overlapping error bars mean that definitive ranking remains an open question. What is not in question is that both belong to the group of the most physically enormous objects in the observable universe. Like V Canis Majoris, U Scuti is classified as a red hypergiant. Its surface temperature is approximately 3,300 Kelvin, and its luminosity is estimated at roughly 300,000 times that of the Sun. It pulsates, varying in brightness over a period of approximately 740 days, one of the characteristic behaviors of highly evolved unstable red giants and hypergiants in the late stages of their lives. U Scuti loses mass at a prodigious rate, continuously shedding its outer layers into a surrounding nebula through a dense stellar wind. The star is estimated to have lost a significant fraction of its initial mass over its lifetime, stripped away before the inevitable final collapse. Some of this material has already been detected in the form of a surrounding envelope of gas and dust that contributes to the star's visual obscuration and complicates precise measurement of its properties. What would it mean to observe wee Scuti from a vantage point comparable to Earth's distance from our own Sun? The star's surface would fill approximately 1/3 of the entire sky in every direction. Its diffuse outer layers would blend imperceptibly into the surrounding interstellar medium with no sharp edge visible, only a gradual fading of reddish glow. Not a disk in the sky, but a surface stretching from horizon to horizon, an entire hemisphere of glowing gas. This is a thought experiment, but it forces a useful confrontation with scale. These stars do not merely represent an incremental enlargement of familiar objects, they represent a qualitative transformation in what a physical object can be. 650 light-years from Earth in the constellation, Leo there burns a star of a very different kind. It carries the catalog designation IRC +10216, also known as CW Leonis, and it belongs to a rare and scientifically extraordinary class of objects, the carbon stars. Carbon stars are red giants in the late stages of their evolution, in which the abundance of carbon in the outer atmosphere exceeds that of oxygen. In ordinary red giants, the opposite is true. Oxygen dominates and most of the carbon is locked up in carbon monoxide molecules. But in carbon stars, the long process of helium shell burning has dredged up enough carbon from the interior to overwhelm the available oxygen, leaving a surplus of elemental carbon and carbon compounds in the photosphere. The result is a star that appears distinctly redder than other giants of comparable temperature, its light filtered through layers of carbon dust that absorb blue wavelengths and transmit red. CW Leonis is one of the closest and most luminous carbon stars to the solar system, which makes it by far the most extensively studied member of this class. Its radius at the peak of its pulsation cycle reaches approximately 500 to 560 times the radius of the Sun, placing its surface at a distance roughly 2.5 times the Earth-Sun separation if positioned at our solar system center. Its surface temperature is approximately 2300 Kelvin, less than half that of the Sun, making it one of the coolest stellar surfaces ever measured. Despite this low temperature, CW Leonis radiates roughly 8,500 times the Sun's total luminosity, a consequence of its immense surface area. The star pulsates with a period of approximately 649 days, varying between roughly 6,250 and 11,300 times the Sun's luminosity over each cycle. This pulsation is not a simple expansion and contraction. It is driven by a complex thermodynamic cycle in the outer layers, where nuclear burning alternately ignites and extinguishes on timescales of months, each episode driving material outward and then allowing it to fall back inward under gravity. The outer stellar layers participate in this rhythm like a vast, slow breath, expanding and contracting, brightening and fading, with a regularity underlying the surface chaos. The stellar wind driven by CW Leonis is among the densest known for any evolved giant. Current measurements suggest the star loses approximately 4 times 10 to the 22nd power tons of material every year, roughly 7 times the mass of Earth, stripped away annually in a continuous outflow. Over the course of its post-main sequence evolution, CW Leonis has shed material equivalent to approximately 1.5 times the mass of our entire Sun, building up an extraordinary circumstellar nebula that surrounds the star and extends outward for tens of thousands of astronomical units. This nebula has a chemical richness that astonishes researchers. Spectroscopic analysis has identified approximately 70 different molecular species in the outflowing gas, including carbon dioxide, water vapor, ammonia, and a remarkable array of organic compounds such as benzene and the simplest members of aromatic chemical families. Some of these molecules represent transient gas phase reaction products, others are adsorbed onto the surfaces of carbon dust grains that scatter and absorb light in complex wavelength-dependent ways. The presence of water vapor around CW Leonis was particularly unexpected, and its discovery in 2001 generated significant scientific discussion. Standard models of stellar atmospheres for carbon stars predicted that all available oxygen should be locked into carbon monoxide molecules, leaving no free oxygen to react with hydrogen and form water. The actual detection of significant water vapor in the circumstellar envelope demanded an explanation. The hypothesis that eventually gained support invokes a photodissociation process. Cosmic ray particles and high-energy photons penetrating the outer layers of the stellar envelope dissociate molecules including silicon oxide and carbon monoxide, liberating oxygen atoms that then react with hydrogen to produce water. But this explanation requires a source of ultraviolet radiation penetrating the envelope, and the envelope itself is largely opaque. The resolution may lie in the pulsation-driven dynamics of the outer layers. As CW Leonis contracts and expands, it may periodically create regions of lower density in its photosphere, allowing radiation to penetrate further than a static model would predict. The total mass of water vapor in the atmosphere and outer envelope of CW Leonis has been estimated at several quintillion tons, a figure that sounds enormous but represents only approximately 1/1000th of the star's total mass. The question of whether CW Leonis has planetary companions is unresolved. Observations conducted in 1994 revealed subtle perturbations in the star's motion, and later studies in 2017 detected anomalous displacements of material within the circumstellar nebula. Both sets of observations are consistent with the influence of an unseen companion object, possibly a small red dwarf star orbiting the giant at a distance of roughly 100 astronomical units, taking approximately 100 years to complete a single orbit. If confirmed, this would make CW Leonis a binary system, and the interaction between the giant's powerful stellar wind and the companion's gravity would add yet another layer of complexity to an already extraordinarily rich astrophysical environment. The future of CW Leonis is not uncertain in broad outline. Within the next 10 to 30,000 years, the star will exhaust its remaining nuclear fuel in a series of thermal pulses, brief, intense episodes of helium shell burning that will drive its outer layers outward in an increasingly powerful sequence of expulsions. Eventually, the outermost shells will be released entirely in a final exhalation, creating a planetary nebula. A luminous, expanding shell of ionized gas lit by the intensely hot stellar core now exposed beneath the departed envelope. That core will be a white dwarf. It will carry approximately 80% of the Sun's mass compressed into a volume comparable to Earth, supported against further gravitational collapse by the quantum mechanical pressure of tightly packed electrons. Its surface temperature immediately after formation will reach several tens of thousands of Kelvin, and it will glow brilliantly in ultraviolet and X-ray light, ionizing the surrounding planetary nebula and causing it to fluoresce. Then, slowly over billions of years, it will cool. Within the expanding nebula that was once CW Leonis, the elements synthesized during billions of years of nuclear burning will be distributed through the surrounding interstellar medium. Carbon, nitrogen, oxygen, silicon, aluminum, and in trace quantities, some of the heavier elements generated in the brief extreme conditions of its pulsation history. These elements will become part of molecular clouds. Eventually, they will be incorporated into new stellar systems. Some fraction of them may one day find their way into planets, into atmospheres, into molecules that participate in chemistry far more intricate than anything occurring inside a star. In this sense, CW Leonis is not merely a dying star. It is a forge whose products will outlast it by billions of years. The deaths of such stars are not merely endings. They are a form of dispersal, a redistribution of material that took billions of years to assemble through nuclear processes, released back into the galaxy to begin another cycle. An explosion is a beginning dressed in the clothes of a catastrophe. And some stellar deaths have been witnessed directly from Earth, leaving records in the historical literature that astronomy has spent centuries trying to interpret. The autumn of 15,072. In the skies above Europe, Asia, and the Americas, a new star appeared in the constellation Cassiopeia, blazing with a brightness comparable to Venus, visible in broad daylight, impossible to ignore for any observer who looked upward. Contemporary accounts describe it as unprecedented, a light where no light had been before, neither moving like a comet nor traveling like a planet, fixed firmly among the fixed stars. The young Danish astronomer Tycho Brahe observed this new light with the meticulous precision that would define his career. His careful measurements established that the object showed no parallax relative to the surrounding stars. It was not an atmospheric phenomenon, not an object close to Earth. It was a star. Something in the heavens had changed, and for a generation raised on the Aristotelian belief in the perfect, unchanging nature of the celestial sphere, this was a deeply unsettling discovery. Over the following weeks, the new star faded. By March of 1574, it was gone, returned to invisibility, leaving no trace in visible light. It would not be observed again in this form. What Tycho had witnessed was a type Ia supernova, the thermonuclear destruction of a white dwarf that had accreted sufficient mass from a binary companion to exceed the Chandrasekhar limit. The resulting explosion released energy comparable to the total output of the Sun over 10 billion years, compressed into a few seconds. Today, the remnant of Tycho's supernova is visible to X-ray telescopes as an expanding shell of hot gas roughly 60 light-years across, still rushing outward from the site of the explosion at more than 5,000 kilometers per second. It will continue to expand for hundreds of thousands of years, eventually merging imperceptibly with the surrounding interstellar medium. The observation by Tycho Brahe had consequences that extended far beyond astronomy. His meticulous data on the positions of planets, accumulated over decades, would later be used by Johannes Kepler to derive the laws of planetary motion, which in turn became the foundation upon which Newton's theory of gravity was built. The death of a star, observed in the autumn sky of 1572, contributed indirectly to the birth of modern physics. Stars do not die in vain. 2,900,000 light-years from Earth, a distance so immense that the light currently arriving in our telescopes departed before our species had evolved, before stone tools had been invented. There lies the Triangulum Galaxy, catalogued as Messier 33. It is the third largest member of the local group, a face on spiral that presents its structure to us in unusual detail. Triangulum is seen almost directly from above, rather than at an angle which makes its organization unusually clear. At visible wavelengths, it presents a loosely wound spiral with two main arms emerging from a small, ill-defined central region, extending outward through a disk approximately 50,000 light-years in diameter. This disk shows relatively little central concentration. Triangulum has no prominent bulge, and its core is not dominated by a massive black hole of the sort anchoring most large spiral galaxies. Indeed, one of the most striking features of Triangulum is the apparent absence of a supermassive black hole at its center. Upper limits derived from the motions of central stars place any central black hole at no more than a few thousand solar masses, orders of magnitude less massive than the black holes anchoring the Milky Way and Andromeda. Whether this reflects a genuine absence or merely a limitation of current observational techniques remains an open question. Some models of galaxy formation suggest that Triangulum's smaller size and more isolated evolutionary history may have prevented the development of a central massive black hole through mergers and accretion. The total mass of Triangulum, including its dark matter halo, is estimated at roughly 50 billion solar masses, approximately 1/20th the mass of the Milky Way. It contains an estimated 40 billion stars, far fewer than the Milky Way's 200 to 400 billion, and far fewer still than Andromeda's 1 trillion. But what Triangulum lacks in sheer stellar population, it compensates for in the rate at which it currently produces new stars. Triangulum is one of the most vigorously star-forming galaxies in the local group. Its disk is rich in atomic and molecular hydrogen, the raw material of star formation, and large areas of its spiral arms glow in the pinkish light of ionized hydrogen gas, excited by the ultraviolet radiation of recently born massive stars. The largest star-forming region in Triangulum and one of the largest in the entire local group is designated NGC 604. It lies in the northeastern spiral arm, roughly 900 light-years across, a cloud of hot, ionized gas approximately 40 times the diameter of the Orion Nebula in our own galaxy. Within this single region, more than 200 massive, hot stars have already formed, with a combined luminosity of several million suns. They illuminate the surrounding gas with a brilliance that makes NGC 604 visible even through amateur telescopes on Earth, despite its distance of nearly 3 million light-years. What we observe in NGC 604 is a vast stellar nursery at the moment of peak activity. The hot young stars already formed are blowing powerful stellar winds into the surrounding cloud, carving bubbles and filaments in the gas and triggering the collapse of dense concentrations into new stellar objects. Some of these newly forming protostars will grow massive enough to undergo rapid nuclear burning and end their lives in supernova explosions within a few million years, seeding the surrounding medium with heavy elements and adding new energy to the turbulent interstellar environment. The process is self-referential. The death of one generation catalyzes the birth of the next in a cycle that has been operating within Triangulum for billions of years. Among individual stars visible in Triangulum's arms, several have been studied in detail. One of the most luminous is a massive blue variable designated GR290, sometimes called Triangulum's Hubble-Sandage variable. GR290 belongs to the class of luminous blue variables, massive unstable stars characterized by extreme luminosity and semi-regular brightness variations driven by instabilities in the outer stellar envelope. GR290's luminosity is estimated at several 100,000 times the Sun's output, and it varies by roughly 1 magnitude over a timescale of approximately 500 days. Its progenitor mass almost certainly exceeded 40 solar masses. Within the next few million years, it will very likely reach the end of its evolutionary trajectory in either a hypernova explosion or a direct collapse to a black hole. The central region of Triangulum, though lacking a supermassive nuclear black hole, contains its own notable objects. Multiple compact X-ray sources, candidate stellar mass black holes and neutron stars in binary systems have been identified in the galaxy's inner zone. The most remarkable is a system designated M33X-7. This object consists of a massive O-type star orbiting a black hole with a mass of approximately 15.5 solar masses, making it the most massive stellar mass black hole with a directly measured mass at the time of its characterization. The primary star has a mass of about 70 solar masses, making this one of the most extreme known examples of a high-mass X-ray binary. Every few days, the primary star passes in front of the black hole as seen from Earth, producing a measurable eclipse in the X-ray light curve and allowing precisely determined orbital measurements. M33PEX-X7 raises a perplexing theoretical question. Standard models of stellar evolution predict that a star massive enough to produce a 15 solar mass black hole should have been losing mass through a stellar wind so rapidly that by the end of its life, insufficient mass would remain to produce such a heavy remnant. The existence of this system implies either that models of mass loss in very massive stars require revision, or that some other mechanism, perhaps interaction between the binary stars at an earlier evolutionary stage, altered the expected trajectory. It remains one of the more intriguing puzzles in stellar astrophysics. Triangulum is not isolated within the local group. Its motion relative to both the Milky Way and Andromeda suggests a complex gravitational relationship. Some dynamical models suggest that Triangulum may be experiencing its first infall toward the local group from the field, a new arrival in gravitational terms rather than a long-standing bound member. Other models indicate that Triangulum has already completed at least one close approach to Andromeda and shows tidal distortions consistent with gravitational interaction. If the latter scenario is correct, some of the structural peculiarities of Triangulum, its unusually extended outer disk, certain asymmetries in its spiral arms, may represent after effects of past encounters rather than pristine internal evolution. The future of Triangulum within the local group merger is uncertain. In approximately 4 to 5 billion years, when the Milky Way and Andromeda begin their final gravitational approach and subsequent coalescence, a process requiring several billion years of multiple passes before the two systems settle into a merged elliptical galaxy, Triangulum may be drawn into the drama. It may ultimately be captured and incorporated into the merged system, adding its 40 billion stars to the new object's population. Or it may be ejected by the dynamics of the encounter, sent outward into the field. At present, no simulation has produced a definitive answer. What is certain is that Triangulum, for all its modesty in the local group context, contains within itself a microcosm of the same processes governing larger systems: star formation, stellar evolution, the recycling of matter, the formation of compact objects, and the slow gravitational dance between components. Its study has contributed disproportionately to our understanding of the local universe. To go further, to cross the boundary from individual galaxies to the large-scale structure of the cosmos, requires first standing back and grasping what lies between us and the structures we are approaching. Consider the Sun. At approximately 8 light minutes from Earth, it is the most familiar star, the foundation of our biosphere. The outer boundary of its gravitational dominance, the heliopause, where the solar wind gives way to the interstellar medium, lies at roughly 100 astronomical units. Beyond, it begins interstellar space, a medium of extraordinary rarefaction, where the average density is roughly 1 hydrogen atom per cubic centimeter. In truly empty regions, the density drops to 1,000 of that value or less. The Sun currently moves through a particular region of this medium known as the local bubble, a cavity in the interstellar gas roughly 300 light-years across, swept clear of dense material by one or more supernova explosions over the past 10 to 20 million years. The bubble is not empty, it contains diffuse hot plasma at temperatures of several million Kelvin, a residual glow from the ancient explosions that carved it. But it is far more tenuous than the surrounding interstellar medium, and its existence means that the solar system has been traveling through unusually transparent space for millions of years. The nearest star system to the Sun is Alpha Centauri, a triple system at approximately 4¼ light-years distance. The typical distance between stars in our region of the Milky Way is several light-years. In that space, empty by the standards of the planetary scale but populated from a cosmic vantage point with an average stellar density, the interstellar medium flows. Its total mass, including the dark matter halo, is estimated at perhaps 1 trillion solar masses. The disk is surrounded by a vast, diffuse halo of older stars, globular clusters, and dark matter extending hundreds of thousands of light years outward. Beyond the Milky Way, the local group extends across a volume roughly 10 million light years in diameter. This is already a scale that strains comprehension, but it represents only the beginning of the hierarchy. The local group is embedded within the Virgo supercluster, also called the local supercluster, a collection of roughly 100 galaxy groups and clusters spread across approximately 100 million light years. The Virgo cluster at the core lies approximately 54 million light years from the Milky Way and contains over 1,300 galaxies, including several giant elliptical galaxies whose masses dwarf anything in the local group. The total mass of the Virgo supercluster is estimated at approximately 1 quadrillion solar masses, equivalent to roughly 1,000 Milky Ways. Its gravitational influence reaches across the local group and beyond, creating a net inward pull that adds a small but measurable component to the motion of galaxies, including our own. This gravitational contribution, sometimes called the Virgo attractor, is detectable in careful measurements of galaxy velocities throughout the supercluster region. But the Virgo supercluster is itself not the largest supercluster structure to which we belong. In 2014, a team of researchers analyzing the three-dimensional flow of galaxies through the surrounding cosmic environment identified a larger structure, one defined not by the concentration of galaxies, but by their gravitational flow pattern. This structure, named Laniakea, encompasses approximately 100,000 galaxies in a volume roughly 500 million light-years across. The Virgo supercluster is just one component of Laniakea. At Laniakea's gravitational center lies a concentration called the Great Attractor, a region of anomalously high mass density located approximately 250 million light-years from the Milky Way in the direction of the constellation Centaurus, partly obscured by the disk of our own galaxy. Beyond the boundary of Laniakea, the supercluster structures continue. Adjacent to our local cosmic neighborhood lies the Perseus-Pisces supercluster, a long curved chain of galaxy clusters extending for approximately 300 million light-years, one of the most prominent large-scale structures visible in galaxy surveys of the nearby universe. But between us and this distant chain, and in other directions around us, the structure of the cosmos changes character abruptly. Between us and the denser portions of the Virgo supercluster, and in other directions as well, lies an extensive region of markedly lower galaxy density. This region, the local void, has a diameter of approximately 150 million light-years and contains far fewer galaxies than the surrounding supercluster environment. The Milky Way sits near one edge of this void, approximately 70 million light-years from its center. The local void is not entirely empty. A handful of isolated galaxies dwell in its depths, too far from any supercluster filament to interact meaningfully with other systems. One of these, NGC 6503, a small spiral galaxy discovered in 1854 in the constellation Draco, sits embedded in the void's interior, roughly 17 million light-years from Earth. In images, it is a delicate multicolored object, blue-tinted spiral arms dotted with pink knots of ionized hydrogen, a brownish core obscured by dust lanes, all set against the black background of an unusually empty region of space. It has been described as a galaxy sitting in a kind of astronomical nowhere. The emptiness of the local void is not a random fluctuation. Like all large-scale voids, it reflects the initial conditions of the universe itself. In the first hundreds of thousands of years after the Big Bang, the universe was filled with a hot, dense plasma in thermodynamic equilibrium. Subtle density fluctuations, imprinted by quantum processes during an earlier epoch of rapid expansion, created slight variations in this plasma. Where the plasma was marginally denser, gravity worked harder over billions of years, building up the filaments, sheets, and clusters we observe today. Where the plasma was marginally less dense, gravity pulled material outward, evacuating those regions and deepening them into voids. This process, gravitational amplification of primordial density fluctuations, is the fundamental explanation for the cosmic web. The vast network of galaxy filaments and walls interspersed with voids that constitutes the largest scale structure of the observable universe. The voids are not accidental, they are as intrinsic to the cosmic web as the filaments that bound them. In 1981, a team of astronomers led by Robert Kirshner at the Harvard-Smithsonian Center for Astrophysics was conducting a systematic survey of galaxy redshifts in a section of sky centered on the constellation Boötes. The goal was to map the three-dimensional distribution of galaxies in that region of space, to understand how galaxies cluster and how their clusters relate to one another. What the survey found was not what anyone had anticipated. In a region covering approximately 3% of the sky, the astronomers found almost no galaxies. Where hundreds of redshift measurements should have populated a volume of space with the expected density of galaxy groups, there were instead only a handful of detections. The void they had discovered extended across approximately 330 million light-years, a nearly spherical volume of space almost completely devoid of luminous matter. The Boötes void, as it came to be known, immediately became one of the most discussed features of the large-scale cosmic structure. Its existence posed a challenge to cosmological models of the time, which had not predicted that voids of such extreme scale and emptiness could exist within the standard framework of structure formation. The answer, developed over subsequent decades, involves the character of the initial perturbations combined with the effects of dark energy. The earliest surveys of the Boötes void were followed by more comprehensive redshift catalogues, which eventually identified approximately 60 to 70 galaxies within the void, but the density there remains dramatically below the cosmic average. And more importantly, the void is understood to be part of the hierarchical structure of the cosmic web, where supervoids are bounded by supercluster walls on multiple sides. The boundary of the Boötes void is marked by some of the most visually striking contrasts visible in large-scale structure surveys. On one side lies a wall of galaxy clusters, including components of the Perseus-Theseus supercluster chain. On other sides, additional filaments and sheets define the edges of this immense empty region. The transition from void interior to surrounding structure occurs over scales of only a few tens of millions of light-years, remarkably sharp by cosmic standards. Imagine, hypothetically, placing an observer at the center of the Boötes void. Instead of the familiar sky populated by millions of galaxies visible in deep exposures, the sky would be almost entirely dark. The nearest large galaxy clusters, 300 million light-years in every direction, would appear as faint, distant smears. The cosmic web, so visually obvious in maps of the full large-scale structure, would be represented only by a distant luminescence on the horizon of the observable region. A wall of galaxies so remote that even with the most powerful telescopes, only the brightest members would be detectable. This isolation would not be complete. Even within voids, the expansion of the universe continues. Galaxies located inside a void are not stationary. They are carried outward by the Hubble flow. But the local gravitational environment within the void differs from that in a filament or cluster. In dense environments, galaxies interact frequently, merging, stripping gas from one another, triggering bursts of star formation. In the void, galaxies are isolated, evolving largely undisturbed, and the void continues to grow. Measurement of galaxies near void boundaries shows that they tend to move outward from the void centers. Their peculiar velocities betray the slow ongoing drainage of the void's interior. Over timescales of billions of years, the Boötes void will grow somewhat larger as material migrates toward the surrounding filaments. The cosmic web is not static. It is an ongoing process of slow gravitational sedimentation, and the voids are its most visible expression of the regions that gravity is gradually abandoning. The Buddha's void is not entirely exceptional within the catalogue of large supervoids. The Eridanus supervoid, located in the southern sky approximately 7 to 10 billion light-years from Earth, spans perhaps 500 million to 1 billion light-years and has been identified in connection with a well-documented anomaly in the cosmic microwave background, the ancient light left over from the Big Bang, now cooled to a temperature of approximately 2.7 Kelvin that permeates all of space. In the direction of the Eridanus supervoid, this background radiation is measurably colder than its surroundings, approximately 70 microkelvin below the average, a deviation roughly 4 times larger than any comparable anomaly previously detected in the microwave sky. The physical mechanism proposed to explain this cold spot involves an effect known as the integrated Sachs-Wolf effect. As photons of the cosmic microwave background travel through a large void, they gain energy when entering the void and lose energy when exiting it. But in a universe pervaded by dark energy and undergoing accelerating expansion, the void is slightly shallower when the photon exits than when it entered, because the expansion has diluted the gravitational well. The photon therefore loses slightly more energy leaving the void than it gained entering it, producing a net energy deficit, a cold spot in the microwave background radiation. However, calculations based on the measured properties of the Eridanus supervoid can account for only approximately 1/4 of the observed temperature deficit. The remaining 3/4 of the anomaly require either a larger or more empty void than the observations directly reveal, or additional contributing factors. Some researchers have proposed that dark matter or dark energy concentrations inside the supervoid might produce gravitational effects not captured by standard models. Others have suggested that the cold spot may represent a primordial quantum fluctuation from the earliest moments of cosmic history, a relic imprinted during the inflationary epoch that expanded the universe in its first fractions of a second. No explanation has achieved consensus. The Eridanus cold spot remains one of the more actively discussed puzzles in modern cosmology. A reminder that even the most well-mapped features of the universe can harbor questions that current science cannot fully resolve. But even the Buddha's void, 330 million light-years across, represents only a middle scale within the full hierarchy of large-scale structure. The largest known structures in the observable universe are not individual voids or clusters, but the immense walls and filaments that bound them, structures whose dimensions begin to approach a substantial fraction of the observable universe itself. The Sloan Great Wall, identified in 2003 from data collected by the Sloan Digital Sky Survey, extends for approximately 1.4 billion light-years, a sheet of elevated galaxy density that required light more than 1 billion years to traverse. For several years, it was considered the largest known structure in the universe, and its existence immediately prompted debate about whether such a concentration could have formed through standard gravitational processes in the time available since the Big Bang. The cosmological principle, one of the foundational assumptions of modern cosmology, holds that on sufficiently large scales, the universe is homogeneous and isotropic, statistically the same in all directions, with no preferred location or orientation. Structures so massive that they could not have formed from initial density perturbations within the available cosmic time would represent a genuine challenge to our understanding of cosmic evolution. The Sloan Great Wall fits within the theoretical limits, though not comfortably. The same cannot be said with confidence for what may be the largest structure ever tentatively identified in the observable universe, a region of anomalously elevated concentration of gamma-ray bursts known as the Hercules Corona Borealis Great Wall. Gamma-ray bursts are among the most energetic events in the universe. Catastrophic explosions associated with the deaths of massive stars or the merger of compact objects, releasing tremendous energy in seconds or minutes. They are detectable across cosmic distances and serve as tracers of galaxy density. Where there are more galaxies, particularly young, star-forming galaxies, there tend to be more gamma-ray bursts. In 2013 and 2014, analysis of the spatial distribution of gamma-ray bursts detected by orbiting observatories revealed an anomalous concentration in a region of sky spanning the constellations of Hercules and Corona Borealis. This concentration appeared statistically significant, far more bursts than expected from a random distribution, and appeared to mark the location of an unusually large structure at a distance of approximately 10 billion light-years. If genuine, the Hercules Corona Borealis Great Wall spans approximately 10 billion light-years. At that scale, even the term structure becomes philosophically uncertain, since at those distances, the Hubble expansion itself begins to blur the distinction between a coherent object and a chance projection along the line of sight. The scientific status of this putative structure remains actively contested. Critics have argued that the sample of gamma-ray bursts in the relevant distance range is too small to establish a statistically reliable conclusion. Detection biases in gamma-ray burst surveys, arising from non-uniform sensitivity of detectors and the difficulty of confirming distances for faint events, may mimic the appearance of large-scale structure where none exists. Independent confirmation from direct galaxy surveys at 10 billion light-years is difficult because at that distance only the most luminous galaxies are individually observable. Nevertheless, the possibility remains open. If confirmed, the theoretical implications would be profound. A structure 10 billion light-years across would span a significant fraction of the observable universe, whose total radius is approximately 46 billion light-years. Its existence could only be explained if the initial density perturbations of the early universe were not scale invariant, if there was more structure at large scales than standard models of cosmic inflation predict, or it could reflect properties of dark energy not captured by current cosmological frameworks. The universe at this scale is not merely revealing structures, it is revealing questions. We began this journey at Saturn, a planet whose rings, laid out across hundreds of thousands of kilometers, once seemed to us the very definition of cosmic extravagance. A world surrounded by billions of ice particles, corralled by shepherd moons, divided by gravitational resonances, sculpted by dynamics that took 4 billion years to arrive at their current configuration. From there, we moved to a young planetary system still in the chaos of assembly, where worlds are emerging from a disk of raw materials around the star. Not yet 1% the age of our own. We visited stars so large that our sun would be invisible within their volumes, objects consuming the equivalent of entire planetary masses every year through stellar winds, maintaining their existence by a precarious balance between nuclear fire and gravity, tipping slowly toward their inevitable collapse. We passed through the death of a star witnessed from Earth, an event whose light took thousands of years to reach us, and whose observation by a young Danish astronomer in 1572 contributed through a chain of intellectual consequence to the foundations of modern physics. We crossed the gulf to a neighboring galaxy, a system containing 40 billion suns, with its own factories of stellar birth, its own extraordinary compact objects, its own chapter in the long history of cosmic assembly. And we arrived finally at structures so immense that they push against the limits, not just of observation, but of the models we use to understand what the universe is and how it came to be, voids spanning hundreds of millions of light years, walls stretching across billions, a putative structure at the edge of the observable cosmos, whose very existence challenges assumptions that underwrite the most successful physical theory ever constructed. What does it mean to know these things? In one sense, very little changes. Our everyday lives occur at scales so far removed from supervoids and hypergiant stars that no direct connection seems accessible. The knowledge that we live on a small planet in an ordinary galaxy, in a relatively sparse corner of the local supercluster, near the edge of a void 150 million light-years across, changes nothing about the texture of an ordinary morning. And yet, in another sense, it changes everything. The universe is not a static backdrop to human experience. It is a dynamic, evolving, extraordinarily structured place whose history is written in the positions and motions of every galaxy, every star, every particle of dust floating in the interstellar medium. Each atom forming the human body was synthesized in the interior of a dying star. Each galaxy visible in the night sky is moving under the influence of structures we are still learning to describe. Some of these structures we have now seen. Others remain beyond our current instruments, waiting for the telescopes and methods of the next generation. Still others may exceed the limits of what any observation could ever reveal, lost beyond the edge of what the expansion of the universe will ever make accessible. The study of the largest objects in existence is not an indulgence. It is the deepest attempt our species has made to understand where we are and what this astonishing architecture, distributed across billions of light years of space and billions of years of time, ultimately amounts to. The investigation continues,